Welcome, fellow chemists, to the third video on the reactions of the alkynes. This is the midway point of the series, so reach out to me via email, social media, or in the comments with suggestions for future videos. Today we will investigate the addition of water. As I've done before, I suggest you watch similar videos regarding hydration of alkenes, so pause this video and watch both acid catalyzed addition and oxymercuration. Links above and in the description. You're back? Let's get started. I suggested watching the acid catalyzed reaction with alkenes because, surprise, with alkynes the process also occurs in the presence of an acid. When the water is fully added, there is an OH group on an alkene. The name of this type of structure is a combination of alkene and alcohol, which gives us the name enol. It's that easy. Well, not that easy. The mechanism certainly is because it's the same as with an alkene, but the enol you see is not the final product. Because a bit of chemistry magic happens and we get a ketone as the final product. Though even that's not completely true, as there is an equilibrium between the ketone and enol. Luckily, in most cases, it favors the ketone so much we don't even bother with the enol, so I won't, though I'll talk more about this magic process in a bit. For internal alkynes, we get one product or an equal distribution of two. If we start with symmetrical hex-3-ine and the alcohol lands on the left carbon, we get hexan-3-one as the product after the magic happens. When the alcohol group lands on the right carbon, it may look like the product will be hexan-4-one, but apply nomenclature rules and it is hexan-3-one once again. In acid catalyzed addition, the alcohol is equally likely to land on the left carbon or right carbon. However, when alcohol lands on the left sp carbon of asymmetrical pentan-2-ine, the product is pentan-2-one. But if it landed on the right carbon, the product is pentan-3-one. Although hydration works with an acid catalyst and internal alkyne, it will not work with terminal alkynes. For success, we bring in everyone's favorite mercurial element, mercury. How it works is quite similar to oxymercuration, and the product is what we would expect. So we have seen much of this mechanism, and like oxymercuration, it begins with the formation of a mercurinium ion. This similarity is why I recommended the video earlier. Next up, water comes in and attacks the most substituted sp2 carbon. When complete, the structure we have is protonated. Another water swoops in and removes the proton. So what exactly do we have now? Well, the intermediate is composed of three parts: mercuric, ene, ol. Well, we know with an enol a bit of magic occurs, and when it is done, the mercuric enol has now become a mercuric ketone. Very quickly, H+ reacts with the oxygen and mercury gives up a pair of electrons. The result is just an enol. As before, when we have an enol, we expect a bit of magic, which ultimately results in a ketone. We have finally reached the end of this process, and the product is butan-2-one. Since I'm no magician, I can safely reveal the secret to the enol-ketone conversion known as tautomerization. Let's look at the acid-catalyzed version. Starting with an enol, the double bond provides electrons for the electrophilic H+, and at the same time, oxygen donates a pair of electrons to a carbon, forming a new double bond. We know oxygen is not commonly found with this positive charge, so what happens next is a water molecule removes the hydrogen from the oxygen, and the oxygen keeps the electrons. At the end of this process, we have the acid and a ketone. The ketone and enol, which are a special pair of isomers called tautomers, exist in equilibrium. Most often, though, the ketone is more stable and therefore dominates product distribution heavily, which is why it is typically shown as the only product. As in all things organic, this may be true most of the time, but do not get caught out by the exceptions. In summary, the addition of water is literally the addition of a water molecule across the triple bond. The initial product is an enol which, through tautomerization, interconverts to a ketone. The ketone is the one that dominates at equilibrium. If the alkyne is internal and symmetrical, the use of an acid catalyst creates only one ketone. If the alkyne is internal but asymmetrical, the use of an acid catalyst produces equal amounts of two ketones. If the alkyne is terminal, a mercuric ion is also needed, and the result is only one ketone. Coming up, hydroboration oxidation, where we try to get the alcohol group to land on that first carbon of a terminal alkyne. I know I have not covered nomenclature of ketones before, and there is a new type of molecule coming in the next video. After the alkyne series is completed, I will make a video or videos about them. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. To prepare for the next video, definitely check out hydroboration oxidation with the alkenes before the one with alkynes is posted.